In this video, I will introduce the idea of stereoisomerism in chirality and determining absolute configuration. So before we get into the specific examples, I'm going to define several terms that I'll use throughout this video to help you understand the jargon when you're looking at stereoisomers. So first of all, a stereoisomer is an isomer, and as we recall from previous instruction, an isomer is a molecule that has the same molecular formula as another. So that is the minimum requirement. And then a stereoisomer specifically is an isomer that has the same connectivity, so it's not a structural isomer, but the orientation of the substituents are different. So in other words, the orientation is different or the three-dimensional structure is different. So the next idea to talk about is chirality, and I'm simply going to talk about how you identify if a center in a molecule is chiral. So to do that, the center is usually a carbon in organic, and that carbon is bound to 4 different groups. We'll talk about how to identify if a group is different, but simply it's just the entirety of the substituent must be different in either structural connectivity or the atoms themselves are different, making them a unique group, and there must be 4 of them for that center to be chiral. There are some exceptions to this. There are some special cases of chirality, but 99% of the time, it's going to be a carbon attached to 4 different groups. So that's what the focus will be here in this video. Okay, so next we have is the Cahn-Ingold Prelog rules. This helps us determine priority of atoms to determine how their three-dimensional space is different. So the Prelog rules are relatively simple. It's just that heavier atoms have higher priority. Sometimes this is introduced in terms of the atomic number, which just means the number of protons in their elemental number, but that corresponds to the weight. So heavier or the higher the atomic number, both of those are sufficient. But the idea is that the larger that number is, either mass or atomic number, the higher the priority that group has. And we'll work through several examples to illustrate this idea, but you just need to know that the Cahn-Ingold Prelog rules is how we determine which substituents, which groups that we mentioned in chirality section have higher priority. Okay, so moving right along, we have absolute configuration. So absolute configuration is the R and S determination that you may have seen previously. And all this means is depending on the priority that we determined from the Cahn-Ingold Prelog rules, the absolute configuration is determined by the direction in which the priority flows. So it's always from highest to lowest. So after you determined your priority, you will then start at your highest group and you will move around in a circle going from 1, the highest, to the next highest, so 1 to 2 to 3, and so on. And the direction that is flowing will determine if it's R or S. If it's clockwise, it's R. If it's S, it's counterclockwise. And there's a little bit of nuance here with the lowest priority group, and this will make the most sense with the examples that I'll work through. But you need to understand that absolute configuration is simply referring to R and S, determination of a chiral center. So next, there are a few specific stereoisomers. One of them is an enantiomer. An enantiomer is a specific stereoisomer with all of its chiral centers opposite. So for example, if this is a relationship between 2 molecules, so if molecule 1 was determined to have 1 chiral center and it was R, its enantiomer would have S orientation at that same carbon. And those would have a structural relationship of an enantiomer. Okay? And again, we'll work through an example to tie this together. And the last idea to understand is diastereomers. Diastereomers are another specific stereoisomer that have 1 or more of their chiral centers that are opposite, but it's very important that not all of them are opposite, because if they're all opposite, that would go back to the enantiomer, which is the previous stereoisomer that we discussed. So by definition, then, a diastereomer must have at least 2 chiral centers, and one molecule may be RS, and then the other molecule will be RR, and the fact that that one position change is what's corresponding to its diastereomer assessment. So with that, let's jump right into several examples. So here we're talking about the Cahn-Ingold Prelog rules. So we need to rank the following in order of priority based on the Cahn-Ingold Prelog rules. So again, this is the heavier atom will have the highest priority. So I have a list of several molecules here, these 6 molecules, and we are asked with identifying which of these 6 is the highest priority and going on and so forth. So first of all, when you're assessing a question like this, we're assuming that we're bound to a chiral center at like this position. So it's like a chiral carbon bound to this OH, a chiral carbon bound to this carbon, and then the rest of the stuff, and so on. So we're just ranking, if these were groups, which one of them would have the highest priority. So what you have to do is look at your periodic table and determine which one has the heaviest mass, and you're looking at the first point of difference. So what I mean is, in all of these, we were comparing the first atom bound to the center. So that means we're comparing oxygen, carbon, 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 and carbon. We ignore the rest of it initially because it's the first point of difference. So right away, we know oxygen is heavier than carbon. So oxygen has higher priority, like group A has higher priority over B. Same with C, same with D, same with E and F. Because oxygen is heavier than carbon, this has the highest priority. So I'm going to go ahead and label it 1 for the highest priority, because the oxygen is the first thing that's different and it's heavier than the counterpart. So we don't have to continue in the substituent if there's already a difference. So moving along then, in B, molecule B, we have a carbon double bound to an oxygen, single bound to another oxygen. So this carbon double bound to an oxygen is the same as this carbon double bound to an oxygen. So right there, there's no difference. Then we continue and we see that this is a carbon bound to 2 hydrogens and another carbon. This is a carbon bound to a hydrogen and then 2 more carbons. This is a carbon triple bound to a carbon. So right away, we know that B and C, since it's bound to a oxygen at least twice, in this case 3 times, in this case twice and once, then these two have higher priority over, B and C have higher priority over D, E, and F, because again, first point of difference. So these oxygens are heavier than the either carbon or hydrogens that the D, E, and F are bound to. So we know B and C are the second and third priority, but now we need to determine among those two which one is the higher priority. So like I've said now, carbon double bound to an oxygen is the same as the carbon double bound to an oxygen here. So then the next difference is the carbon bound to an oxygen, carbon bound to a chlorine. We know that chlorine is heavier than oxygen. So again, first point of difference, this chlorine is heavier than this oxygen. So this is the second priority. And this group then becomes third, because we already determined that these two are more higher priority than D, E, and F. So those have to be 2 and 3, and we just had to figure out among those two which one was 2 and which one was 3. Okay, now let's move to group D. Group D is a carbon bound to 1 carbon and 2 hydrogens. This is a carbon bound to 1 hydrogen and 2 carbons. So this one is heavier right now, relative to D, because it is bound to 2 carbons, whereas this is only bound to 1. So we know that E is higher than D. And this carbon is triple bound to a carbon, which we consider in the Cahn-Ingold Prelog rules, is that this carbon is bound to 3 more carbons. So we consider F to be a higher priority than E. So this would be 4. And then we said that E was greater than higher priority than D. So this is 5. And lastly, there is 6. So you need to be able to do this rather quickly in a molecule to make the absolute determination of absolute configurator determination of R or S. So hopefully this example makes sense. I'll work through several examples of determining absolute configuration, which will always be using the Cahn-Ingold Prelog rules. For the remainder of the video, I'll work through several examples as usual. So here the question is to determine if the following groups are chiral. That is our first task. And then if they are, what is the absolute configuration? So the second part, if they're chiral, we'll tie this all together using the Cahn-Ingold Prelog rules and our idea of absolute configuration. So here, if we look at molecule A, we have to look at each potential chiral center and determine if they're chiral to make this assessment. So first of all, in organic chemistry, like I mentioned before, carbons are usually going to be the center of chirality because they have the opportunity to have 4 different groups on them. So let's first consider this carbon here. This carbon is bound to 2 hydrogens. Those are identical groups, so we know that this carbon is not chiral. If we go to this carbon, it is bound to 1 carbon and 3 chlorines, so we know that this is also not chiral. And this carbon now is the only one that's left to be chiral, and we have to look and see this carbon is bound to 1 carbon, this carbon is bound to another carbon, chlorine and hydrogen. So right away we know chlorine is different from hydrogen. Those are different groups. Now we have to determine if this carbon group is different from this carbon group. So a lot of students get confused here and say that, hey, these are both bound to carbons, that's the same group, and it's not true. Just like in the Cahn-Ingold Prelog rules, we have to check if the entirety of that group is the same. So again, it's looking for the first point of difference. So if we look at this carbon, it's bound to 1 chlorine and 2 hydrogens. This carbon is bound to 3 chlorines. So that's different. So these 4 groups are different. So this is in fact chiral, where the only chiral center is this carbon. And whenever you see these dashes and wedges, that's usually an indication that there's going to be a chiral center at that position, but it's not always the case. So you have to check yourself, but if you see these dashes and wedges, you should certainly check if that position is chiral on your own. It's just kind of an indication that, hey, I should pay extra attention to that carbon because it's dashed and wedged. So since we're on this topic now, whenever you see a dash, that means that that is coming out of the plane. So this hydrogen is coming out of the plane of the paper, and this dash is going into the plane of the paper. So remember, these molecules have 3-dimensional shapes, so it's not like they're all in the plane like we like to draw them. We use these dashes and wedges to illustrate how they would actually, or how they actually exist in 3-dimensional space. Okay. So now that we know that this is chiral, we have to determine using our Cahn-Ingold Prelog rules which of these groups is the highest priority. So right away, we see that a carbon is bound to another carbon, so those are the same. Hydrogen, that is the smallest of these options, and chlorine, that's the heaviest. So right away, first point of difference, we know chlorine is the heaviest group. Then we have a carbon bound to 2 hydrogens and a chlorine, and a carbon bound to 3 chlorines. So 3 chlorines is heavier than 2 hydrogens and a chlorine, so this is second priority. And then this, we know this carbon is heavier than a hydrogen, so that is 3, and this is 4. So now we have to determine which direction the priority is flowing from highest to lowest. So you ignore the lowest priority in this directional assessment. So we have groups 1, 2, 3, that is going this direction, which is clockwise. So that looks like R. Okay, now if the lowest priority, so number 4, in this case, our hydrogen, is in the back. So what I mean by back is if it's a dash, then the absolute configuration is what it appears. But in this, if it's not, then it's the opposite of what it looks like. So since this hydrogen is a wedge and not a dash, then we know the absolute configuration has to be S because it is the lowest priority of the hydrogen is not in the back. So since it's in the front, there's only 2 options of R or S, it has to be S. So this absolute configuration of this chiral center carbon is S. Okay, if, like I'm saying, if the hydrogen was in the back and everything else was oriented the same, then it would look like R and it would be R. Okay, so I know this is confusing. We're going to work through more examples to illustrate this idea, but just know you have to orient yourself where the lowest priority is, and that will determine which direction that you need to give as the final answer. All right, I hope you found this video useful. Be on the lookout for future videos that will explain the relationships of diastereomers and enantiomers. I'll also be working through more examples of determining chirality in more complicated molecules, including Fisher projections and different representations like that. So be checking that out. If you found this helpful, please leave a like and subscribe to the channel for future content. And yeah, with that, I hope you have a good day, and I'll see you all in the next video.